So in today's class, we are going to talk about a very important technique which is called as Danavitt-Hartenberg convention. So Danavitt-Hartenberg method, that is also called as DH method or DH parameters, for forward kinematics. This technique is sort of a plug and chug technique. What it means is, unlike the previous technique we used where we find the rotation matrices, we find the projection matrices, unlike that technique, in here, what we do is we identify certain parameters, follow certain rules, find certain parameters, and then we actually just plug and chug those numbers. But this technique is very famous and used everywhere in robotics textbook. So invariably, all the robotic textbooks use this Danavitt-Hartenberg sign convention. The idea is simple, and initially it may seem a little bit difficult, but once you understand the rules, what you do is you plug and chug. You construct a table and then use the quantities in the table to find the homogeneous transformations. So I'm gonna give you the technique today. I will work out one problem and I'm gonna do it in detail, repeating it multiple times since it's the first problem. And in the next class, I will work out some more problems, because that way you will be familiar with how to solve the problem with DH parameters. And if you really want to check the answers for your homogeneous transformations for quiz 1, and if you're up to it, you can apply this Danavitt-Hartenberg technique to each of those problems, construct the table, and then you can actually use the homogeneous transformation formula that I will give you to find the homogeneous transformation. So in this Danavitt-Hartenberg parameters method or DH technique, we create a table. This table has 4 parameters. One is theta, second one is alpha, then you have R, and you have D. And then if you look at this table has rows, and the number of rows are less than number of joint plus end effector. So for an example, there will be row 1. This row 1 will be responsible, or these parameters we will use to find 0, H1. There will be row 2. So in this row 2, there will be some theta 2, some alpha 2, some R2, and some D2 that will be used to find 1H2. Similarly, there will be a row 3, and in this row 3, you will find theta, alpha, R, and D that would help you construct 2H3. So the most important part is, how do we construct this table? And you already know half of it. So remember the coordinate system rules, coordinate system rules. The coordinate system rules that we talked about is Z must pass through axis. axis, whether it's a rotational joint or it's a translational joint. Then the xn should be perpendicular to zn and zn minus 1. Then xn must intersect zn and zn minus 1. And we should be using the right hand coordinate system. So these are the 4 rules that we have been using so far. Now the idea is we will follow the same rules, but there are additional rules on how do we find out theta, alpha, r, and d. So the question is, how do we find theta, alpha, r, and d for each joint? And what we are going to do is I'm going to define term by term what is theta, what does theta mean, what does alpha mean, what does r mean, and what does d mean. So sometimes they may look a little confusing, but once you get familiar, it will make sense. So everyone understood the idea is, given a robot, say if you are given a robot, step 1 is to add a coordinate system. Say for example, if you have a robot, and I just want to give you a simple robot. This is R, and say there is a P. Now, if the robot is RRP, what we need to do is, first and foremost, we need to follow the 4 rules for the coordinate systems and set up the coordinate system. So this is going to be my Z0, this is going to be my Z1, this is going to be my Z2, and this is going to be my Z3. So you have different coordinate systems, different Z's. Then what you do is you use the rule for X. Here this is X0. Then here it is X1. Then here it is X2. And here it is X3. Now, one thing I want you to note is X0 has to be perpendicular to the current frame and the previous frame. There is no previous frame. X1 has to be perpendicular to the current Z1 and the previous Z1, and it needs to intersect. X2 needs to intersect Z2 and current Z1. One thing I want you to note that X2 is not intersecting with Z1. So we may have to translate the frame later. So if you look at X2 and if you look at Z1, X2 is intersecting Z2, but X2 is not intersecting Z1. X2 and Z1, they are parallel. Then you have X3 and then you have Z3. Then we complete the right angle coordinate system, something like Y0. Then you have Y1. Then you have Y2. You have Y3. So this is the coordinate system. Now, when we are trying to find out the Danavet-Hartenberg coordinate system, I want you to notice, look at the number of joints. So the number of joints are, this is my first joint, this is my second joint, and this is my third joint. So this Danavet-Hartenberg table has 1, 2, 3. It has 3 rows. Look at the number of frames. So there are 4 frames. So DH table will have 4 minus 1, 3 rows. So whenever you are trying to find out a DH parameter, your number of rows should be one less than, they should be equal to the number of joints, and usually they will be less than one less than number of frames. Now what we are going to do is, this is the question, that how do we find out theta, alpha, R and D corresponding to any robot? So what I need to do is, if you look at the robot that I have drawn, there are 1, 2, 3 joints. So I need to fill in total 4 multiplied by 3, 12 elements. So I need to find out theta 1, alpha 1, R1, D1, theta 2, alpha 2, R2, D2. So I will just go ahead, write it down. So I need to find out what is theta 1, alpha 1, R1, D1, what is theta 2, alpha 2, R2 and D2, and what is theta 3, alpha 3, R3 and D3. Now, again, to do this, there are 4 rules. So we'll start with the first rule. So first is, how do we find out theta? Theta and alpha, they correspond to orientation. So I need to write this down. These two parameters are orientation, and these 2 parameters are for displacement. And for theta, theta is defined as amount of rotation about Gn minus 1 axis. Amount of rotation Gn minus 1. Yeah, Ima, it's okay. You can treat it different way. That's totally fine. X2, yeah, you can actually do it like this. Yeah, that's totally cool. X3, Y3. So I just changed the orientation for the last axis. That's totally fine. Okay, so amount of rotation about Zn minus 1, so that, this is very important, so that Xn minus 1 and Xn get aligned. Including joint angle. So what is the physical interpretation of this? Theta is sort of the angular variation between the frame orientation. But if the frame is located on a revolute joint, you would add that joint variable as part of this angular variation. So let me give you an example. So consider that I have Z naught, I have Y naught, and I have X naught. This is one frame, and then I have, and I will work out a few problems so it will be clear. But first, I just want to give you a dummy problem. So you have x n, say zn, yn, or let me say this as xzn minus 1, yn minus 1, xn minus 1. So I have two frames which are both right angle coordinate system. But what I need to know is, first I need to find out the value of theta. And let's do this exercise step by step. I want to find out the value of theta in this orientation. So I should be looking at frame which is n minus 1. So this is n minus 1 frame. N minus 1 frame. This is n frame. And in n minus 1 frame, I should be looking at the axis zn minus 1. So this is the axis. That's what I'm gonna look at. And then I'm gonna see is how do I orient n minus 1 frame. So the question is how to orient n minus 1 frame so that x n minus 1 gets aligned with xn. So now I want you to observe the only way this frame will get aligned, xn minus 1 frame will get aligned, if I rotate about gn minus 1 by 90 degrees. So when I perform this rotation, what's going to happen is my z, and I will show you the modified version of it, zn minus 1 so zn minus 1, then this becomes xn minus 1, and this becomes yn minus 1. So after rotation, after theta rotation, I get this frame which is aligned like this. So theta in this case is going to be 90 degrees. And why is 90 degrees positive? Because check this out. Curl your fingers in the direction of rotation that you are applying, and that direction of rotation is aligned with the positive zn minus 1 axis. That's why this rotation is positive. So everyone understood? So I have two frames, n minus 1 and n. And what I want to do is, I just want to find out how can I align my previous frame to the current frame by applying rotations about previous z, so that xn minus 1 gets aligned with xn. Now, one thing I just want to note here, that for some reason, if there is a revolute joint involved, if n minus 1 frame is at revolute joint, so then that joint variable gets added. So theta 1. So otherwise, you don't have to add the joint variable. So that is rule number 1. So when you are trying to align, you want to align the previous frame to the current frame. Everyone clear about this rule? I'm looking at the chat window, just if you need me to explain, because there are 4 rules, and once you understand those rules, then finding out The homogeneous transformation using DH parameters is very straightforward. Okay, no questions. So I'm gonna go for the second rule. Second rule is, how do we find out alpha? Alpha is also twist or rotation. Alpha is amount of rotation about xn, and this is very important. The previous rotation was about Zn minus 1. Alpha is about Xn, so that Zn minus 1 matches with Zn, with Zn. Now these rules may seem arbitrary, but later we'll gradually think about their applications. So just let me give an example. We found out theta in the case of the second rule. So consider that I have a right hand coordinate system, something like this: Zn minus 1, Yn minus 1, Xn minus 1, and I have the second coordinate system, which is Xn, Yn, and Zn. Rule number 1 is theta 1. We add, yeah, it really depends upon, so I should be very clear. I should be saying here theta n, theta n. So now in the second rule, please understand, again, we have two frames, but notice the rotation is now about xn. So this is the axis of rotation. And now what I need to do is, I need to find out the rotation so that current Zn is aligned with Zn minus 1. And only way this could happen here is by rotation of 90 degrees here. So which means, just to be clear, I need to write Cn is aligned with Cn minus 1. So we are rotating Zn. So the amount of rotation that we need to apply, so that so actually, yeah, so amount of rotation Zn minus 1 is aligned with Cn. So this is super important, and I want you to be very careful about it, because these rotations could be confusing. So now here it is 90 degrees. So when we rotate the 90 degrees, Zn, which is shown over here, Zn gets aligned with Zn minus 1. So Zn, Zn, this is Zn minus 1, this is Zn minus 1. And there is a little bit, oh yeah. Okay, so there are some questions. I just want to be very clear about this rule. So right now, please don't focus on theta rule, just focus on alpha rule. And the reason for alpha rule is the rotations are about two different axes. So first, I want you to note what is going to happen here. So there are two axes. one is Zn and Zn minus 1. The rotation is about Xn. And please hold your questions before I explain these rules, okay? Because if I start explaining the answer to the questions, this may get a little confusing, or I may get confused. So please bear with me. Let me finish the 4 rules and I'll answer your questions. So alpha is the rotation about Xn. And this rotation in such that Gn minus 1 is aligned with Zn. Now, please note here it is Zn minus 1 and here it is Zn. Unlike the previous theta, what we are trying to do is we are trying to rotate about this Xn so that you get the rotation. Now check this out. The only way Zn minus 1 will be aligned with Zn if the rotation is like this. The only way, and when this rotation is applied, what you're going to do is your new coordinate system is going to look like Yn minus 1, Gn minus 1, Xn minus 1. This rule is kind of tricky. So in this particular case, what's going to happen is, yeah, before you start asking question, please let me finish. In this particular case, what's going to happen is your Xn is this. But what you are rotating is not the current frame, but the previous frame. So you are rotating n minus 1 frame. So this is something important. You are not rotating n frame. So you are rotating n minus 1 frame. So now if you look at the n minus 1 frame, and I'm going to highlight that n minus 1 frame, the n minus 1 frame is this. But this frame needs to be rotated about not its own xn minus 1, but xn, which is over here. And if you look at the rotation is clockwise 90 degrees. So if you consider, if you curl your fingers in the direction of 90 degrees, I mean in the direction of rotation, your alpha is going to be 90 degrees. So this is very important. So please understand, theta rule and alpha rule, they are applied at different axes. In the case of theta rule, you are applying the rotation about Zn minus 1, and the rotation is of the same frame. So you apply the rotation about Zn minus 1 and rotate n minus 1 frame. Here the rotation is about Xn, but the frame that is rotated is not nth frame, but n minus 1 frame. So n minus 1 frame is rotated. And thus, if you look at the angular rotation, here the alpha is positive 90 degrees. It's not a negative 90 degrees. So that is the tricky part about this rule, which means you are rotating about xn, but you are not rotating the nth frame, you are rotating n minus 1 frame, but the direction of rotation is determined from xn. Before I proceed further, is everyone clear about this rule? The rotation of theta will be about Zn minus 1. Rotation of alpha would be about Xn. To answer John's question, no, it is plus 90 degrees. It's not minus 90 degrees. Because if you look at the rotation alpha, if you curl your fingers in the rotation, you will see that Zn minus 1 frame gets aligned with Zn when you have a positive rotation of 90 degrees about Xn. Everyone clear about this rule? Oh, I got confused with, I don't see the question. John asked me some question. Okay, once again, if you look at the first rule, theta, the theta is found out by rotating n minus 1 frame. And n minus 1 frame is rotated about Zn minus 1. For alpha, n minus 1 frame is rotated about Xn. So I don't understand what question John is referring to, but this is how it should be. We are not rotating n frame anywhere. We are not rotating n. So, oh, okay. So hold your, that's why. Okay, all right. So all is well. So please hold your horses before asking me questions. Then I will be, so that I don't get confused. Okay, so just for my own satisfaction, theta is when you have two frames, n minus 1 and n frame, and you want to align xn minus 1 and xn, but here the frame that is going to be rotated is n minus 1. So what you need to do is you will have to rotate n minus 1. However, when you are trying to find alpha, you are still rotating z n minus 1 or n minus 1 frame, but that rotation is about xn, and the xn rotation will dictate whether it's a positive rotation or it's a negative rotation. Now the third rule is r displacement is from frame n minus 1 to frame n in xn direction. So once again, let me try this. Cn minus 1, yn minus 1, xn minus 1. And then you have this other frame. And please note, these are the distances. So these are not rotations. So I'm going to say yn, xn, zn. And let's first find out what is the xn direction. Xn direction is this direction. If you travel in this direction, it's positive. If you travel in the opposite direction, it's negative. And imagine that this frame and this frame, they are at different distances. So So for an example, if this distance is say B, this distance will have two components. One component would be along xn, and the other component will maybe is along zn. So I'm just going to draw a three-dimensional figure. I can draw a two-dimensional figure. So you have two distances. So there is one distance here, which is parallel to zn, and the second distance here, which is parallel to xn. So we are looking at this distance. This distance is r. So this is the r distance. So the displacement is between the frame n minus 1. This is frame n minus 1. This is frame n. And the distance is along xn. And please notice this is a positive or negative. So if you are going to go in the same direction as xn, that displacement will be positive. If you go in the opposite direction, it will be negative. Now I need to write down the last rule, which is rule number 4, which is called as d displacement. D displacement is between frame n minus 1 to frame n in zn minus 1 direction. So what it means is, let's consider that we have two frames. This is zn minus 1. This is yn minus 1, xn minus 1. And you have another coordinate system, xn, yn, and zn. So d displacement is between, this is frame n minus 1. This is frame n. And I'm gonna consider 2 points. And the distance that I'm looking at is this distance. This distance is d. So, and please understand, in this case, the distance is between n minus 1 and n frame, but you should be looking at the distance around about zn minus 1. If you go in the positive direction, as the same direction as zn minus 1, that's positive. If you go in the opposite direction, it's negative. Here we are looking at xn. So quickly look at, you have one rule for theta, you have one rule for alpha, you have one rule for r displacement, you have one rule for d displacement. Now let's work out a problem. So our objective is, the very first objective is, so with these rules, so I will write down what the objective is. Objective, with these rules, fill dh parameter table. Let me consider a simple robot. So what we have is, we have a robot. The first revolute joint, then I have a second revolute joint, and then maybe at the end I have a prismatic joint. Now what I'm going to do is, I'm going to use the DH parameters technique to find out the homogeneous transformations. But no matter how you solve the problem, step one is to assign the coordinate system. So Z naught, Y naught, sorry, Z naught, X naught, Y naught, Z1, X1, Y1. Then I have X2, Y2, Z2, and say here I have again X3. This is the end effector. I have X3, Y3, Z3. Now what I'm going to do is, I'm going to add theta 1, then I'm going to add theta 2, then I'm going to add some distance d. So this distance is d. I'm going to add additional distances here. This is A1. This is A2. This is A3. And this is A4. And this we are going to solve for 3 different joints. So I have just copied the figure because I'm going to explain each joint separately. So here is the idea. So what I want to do is, I want to construct the DH parameter table for this robot. This robot has the first revolute joint, it has a second revolute joint, and it has the third revolute joint. And I'm going to construct the table something like this. So I will have theta, alpha, then I will have R, and then I will have D. So theta, alpha, R, and D. And I'm at the first joint. So just for the sake of classification, I'm gonna redraw the coordinate systems. So so right now our coordinate systems are 0th frame and first frame. So let's draw the 0th frame. The 0th frame looks something like this: C naught, X naught, Y naught. And the first frame looks something like Z1, Y1, and x1. So to find theta, what I need to be looking at, so let's look at the rule for theta. For theta, I should be looking at Zn minus 1. So I should be looking at my coordinate frame, which is this. Then second thing, what I should be looking at is I should be looking at the rotation about Zn minus 1. So Xn minus 1 gets aligned with Xn. So, but please note, so the axes that I'm looking at is X0 and X1. So I want to find out the amount of rotation about Z0 that would align X0 and X1 axis. But if you look at the way the figure is constructed, these two frames are already aligned. So which means the alignment is going to be 0. But please note, there is a revolute joint. So whenever you have a revolute joint, you need to include the angle of rotation, which is theta 1. So I'm done with the first value of theta, which is it will be 0 plus theta 1. Now let's apply the second rule. The second rule is the rotation about xn, but the frame that we are going to rotate it's Zn minus 1 so that it gets aligned with Zn. So check this out. Now we are going to rotate. For the second rule, the rotation is about xn, but the frame that needs to be rotated, actually I should draw, let me draw a different frame. So let me show you here. So this is Z0, this is for theta, this is for x0, y0, z0, and here it is x1, y1, z1. So the frame about which we have to rotate is this, but the guy that needs to get rotated is Z0. So I want you to understand that the only way Z0 and Z1 can align if I apply the rotation of 90 degrees. This is for alpha. This is for theta. So the only way, and I want you to visualize, even though I should be very clear, even though this rotation is applied at x1, even though the rotation is applied x1, the frame that is going to get rotated is Z0. So after rotation, your frame is going to be like this. So you will have Z0, you will have Y0, and you will have X0. So finally, Z0 and Z1 that needs to get rotated. So this rotation is 90 degree plus. So you will have plus 90 degrees. The next thing that we have to find out is the distance r, and look at the rule for r. R is the displacement between n minus 1 and n along xn. So xn distance, and I will try to show it over here. Xn is this. R is the distance between the previous frame. So the distance is going to be A2. So this is the distance between the previous frame and the current frame along xn. So this is going to be A2. And D2, let's look at the D2. D2 is the distance between the current frame and the previous frame along Zn minus 1. So this is the current frame, previous frame, and the distance that is along Zn minus 1 is A1. So that is how you can find out the first parameter, or the first the row of the DH parameter table. Now let's look at the second frame. So now I'm looking at theta, alpha, R, and D. Theta, alpha, R, and D. And what you have is, you are at joint 2. So you have, it should be between 2 and 3. One thing I just want to let you know is, if you look at the frame 2 and frame 3, the one rule is not satisfied. If you look at x2, x2 is perpendicular to z2, x2 is perpendicular to z1, but x2 is not intersecting with z1. x2 is intersecting with z2. So what we need to do is, we need to translate the frame so that this coincides. So we have to translate the frame so that this coincides with x2, z2, and y2. So frame translation, because x2 not intersecting z1. So we did the frame translation, and for finding out theta, alpha, R, and D, we use translated frame. We use translated frame 2 and frame 1. So let me draw these frames. So look at, just for the sake of clarity, I have x2, I have, let me draw the x1, y1, z1 plus first. So I have y1, I have z1, and I have x1, and then I have this x2, I have z2, and I have y2. So these two frames. Let's look at the theta. The theta has to be about Zn minus 1. So look at the theta rule. Theta is amount of rotation about Zn minus 1, so that the Xn minus 1 gets aligned with Xn. So let's find out the rotation. So the rotation is going to be about Z1, and what rotation I need to apply, so that the x1 gets aligned with x2. So, and as you can see, the only way x1 can get aligned with x2 is by 90 degrees. So theta is going to become 90 degrees. So for theta 2, 90 degree, positive 90 degree rotation about Z1 needed to align x2 to x1. So that is, once you rotate, that is, actually I need to be very clear, x1 to x2, x1, x2. And then there is a joint variable. So I'm going to add theta 2. Now let's look at the alpha. The rule for alpha is the amount of rotation that is needed about xn so that the zn minus 1 matches zn. So the amount of rotation about xn, and in this case xn is nothing but x2. Amount of rotation that is needed is about xn, which is x2, so that zn minus 1, in our case this is zn, matches with z1 matches with z2. So let's see z1. Where is z1? Is over here, and z2 can only be matched by plus 90 degrees. So alpha 2 is 90-degree rotation needed about x2 so that z n minus 1, which is z1, matches with z2. So you have 90 degrees here. Now let's look at the third rule for alpha, for r. R is the distance between frames along xn. So let's look at xn. But since these two frames are aligned, the distance between those two is 0 because we are looking at the translated frame. So I need to write this down here. Since we are looking at the translated frames, these distances are 0. R is 0 and D is 0. If you look at the kinematic diagram that I have drawn, originally x2, y2, z2 was by distance a3 apart from a frame 2, a frame 1. But since we translated the frame to meet all the 4 rules, the effective distance is 0. Now we have to form the last column of the DH parameter, last row of the DH parameter, which is theta, alpha, r, and d. Now for the last column, for the last row, I should be looking at the frame number 2 and frame number 3. So check this out. My frame number 2, translated frame number 2 is here. Y2. So this is translated frame number 2. Now please note that we have to follow the same rules that we talked about. Now what we need to do is we need to go back to the rules and let's find out the value of theta. The theta is the rotation about z n minus 1 so that x n minus 1 gets aligned with xn. So let's rotate. Let's look at the rotation z n minus 1, and for that, this is my rotation. This is z2, And now you can see that the rotation what is the rotation about Z2 so that X2 and X3 get aligned. And the only way they can get aligned is if I have the rotation, negative 90-degree rotation about Z2 axis. So I'm going to write this down here just for satisfaction. Z2, this is X2, this is Y2, and the second frame is Z3, X3, Y3. Now what I'm looking at, the rotation about Z2 so that Z2 so that the X3 and X2 get aligned. But if you think about the way I have drawn this, they are already aligned. So I don't have to worry about it since X3 and X, so that X3 and X2 get aligned. So X3 and X2 are already aligned. So I will get 0 here. There is no joint angle. There is just a prismatic joint variable. So there is no theta 3 as to speak. So we can move on to alpha. So to find alpha, we have to use the second rule. You have to look at the rotation about xn, which is x3, and rotate zn minus 1, which is z2, so that z2 gets aligned with z3. So now I'm looking at the rotation about x3. I'm going to draw this again for reference. X2, Z2, Y2, you have Z3, X3, Y3, and now my rotations are going to be around X3. So this is for alpha. The rotation will be along X3, but the frame that I want to rotate, is the previous frame. So I need to rotate Zn minus 1, so Z2, so that it gets aligned with Z3. But if you look at Z2 and Z3, they are already aligned. So my alpha becomes 0. Now R is the distance between uh, the previous frame and the current frame along xn. So the distance between the previous frame and the current frame, the previous frame is x2, y2, z2, x2, y2, z2, which is located here. And the current frame is this. So these are the two frames that we are considering. And I'm interested in looking at the distance along R. Please note, which is around x, that distance is 0. So the distance between these two frames along xn, which is along x3, is 0. Last but not least, I'm interested in finding out the displacement between the old frame and the new frame along Zn minus 1. So the old frame and new frame along Zn minus 1, which is nothing but Z2, and that frame, so along Z2, that distance, this is Z2. So just so that this is for last, that is A3 plus A4, A3 plus A4 plus D. So now if I look at my total DH parameter table, my DH parameter table is going to look like, you will have theta, alpha, R, and D. And you will have 1, 0, plus theta 1, 90, A2, A1, 2, 90, plus theta 2, 90, 0, 0. And the last is going to be 3, which is 0, 0, 0, 0, 0, 0, A3 plus A4 plus D. This is how you complete the DH parameter table. And once the DH parameter table is completed for any joint, the last thing is just plug and chug. So let me give you a classic formula. So if you are trying to find out a homogeneous transformation between n minus 1 h n, this homogeneous transformation is given as cosine theta n, sine theta n, 0, 0, minus sine theta n, cosine alpha n, cosine theta n, cosine alpha n, sine alpha n, 0, sine theta n, sine alpha n, minus cosine theta n, sine alpha n, cosine alpha n, 0, Rn cosine theta n, Rn sine theta n, dn, and 1. So now what we need to do is, we need to appropriately select the values and something like this. So if I'm interested in 0, h1, the row I should be looking at is this, and this row I find out the first homogeneous transformation matrix as cosine theta 1, sine theta 1, 0, 0, minus sine theta 1, cosine alpha 1, which is 90, cosine theta 1, cosine of alpha 1, which is 90, sine of alpha 1, 0, sine of theta 1, sine of alpha 1, minus cosine of theta 1, sine of alpha 1, cosine of alpha 1, 0. The last one is Rn, which is A2, cosine of theta 1, Rn A2, which is sine of theta 1. Then you have D, which is A1, and then you have 1. So that is how the first homogeneous transformation matrix gets formed. And you can just write this equation, 0h1 is equal to cosine theta 1, sine theta 1, 0, 0. Cosine of 90 degrees is 0, so you get 0. Cosine of 90 degrees is 0, you get 0. Sine of 90 degrees is 1, so you get 0. Here sine of 90 degrees is 1, so you get sine theta. Sine of 90 degrees, so it become minus cosine theta 1. Cosine of 90 degrees is 0. 0, you get A2 cosine theta 1, A2 sine theta 1, A1, 1. So now you see that the same formula that we derived for the homogeneous transformation using our rotation matrices is coming up. Similarly, you can formulate 1H2. To find 1H2, what you need to do is you need to grab the thetas, r's, d's from the second row, and that becomes cosine theta 2, sine theta 2, 0, 0, minus sine theta 2, cosine theta 2, sine of 90 degrees, sine of 90 degrees, 0, sine theta 2, sine of 90 degrees, minus cosine theta 2, sine of 90 degrees, cosine of 90 degrees, 0, and then the R2 and D2s are zeros, so you will have 0, 0, 0, 1. So your 0H1 matrix can be written as cosine theta 2, sine theta 2, 0, 0, sine theta 2, sine 90 is 1, cosine theta 2, sine 90 is 1. So, and then here you would get sine theta, sine theta. I think I made a mistake in here while plugging the values. So 0, 0. So just check my, when you plug in the values should be cosine theta 1. So cosine theta 2, sine theta 2, and alpha in this case is 90 degrees. So alpha equal to 90 degrees. Theta is 90 plus theta 2. Theta is 90 plus theta 2. R is equal to 0. R is equal to 0. And D is equal to 0. So yeah, actually I think you will need to plug this in again. I will rework out this plugin problem again because we are past time. So what we need to do is for H2, H12, we will have to substitute the value of alpha is equal to 90, theta is equal to 90 plus theta 2, and then formulate the equation. Just for the sake of completion, I will try to complete this. So 1H2 is equal to cosine of 90 plus theta 2 minus sine of 90 plus theta 2 cosine of 90 degrees, sine of 90 plus theta 2 sine of 90 degrees. R is 0. The second one is going to be sine of 90 plus theta 2. Then you are going to have cosine of 90 plus theta 2, cosine of 90. You are going to have cosine of 9 minus 90 plus theta 2 and sine of 90, and you're going to have 0. Then you're going to have 0 sine of 90. Then you're going to have cosine of 90. Distance is 0, and you're going to have 1. 0, 0, 0, 1. This is how it should it should actually look like. And then you can use the sine and cosine trig identities to convert into minus or plus, just like Trenton said. And the last one, and I will write this over here, so which is 2H3. And for 2H3, remember our theta, alpha, r, all the values are 0. So theta is equal to 0, alpha is equal to 0, r is equal to 0, but d is equal to A3 plus A4 plus D. A3 plus A4 plus D. So what I'm going to do is I'm going to substitute these values. So this will become cosine of 0 minus sine of 0, cosine of 0, sine of 0, cosine of 0, cosine of 0, 0, sine of 0, 0, 0. This will become sine of 0, sine of 0, minus cosine of 0, sine of 0, cosine of 0, 0. And then I'm going to have 0 here. I'm going to have 0 here. And I'm going to have A3 plus A4 plus D. And I will have 1 over here. So finally, 0H3 is equal to 0H1, 1H2, and 2H3. And you can perform these calculations in MATLAB and you will get the same answer. Okay, I'm going to stop here. If you have any questions, I would be happy to answer.